There's a secret at the heart of modern physics that almost nobody talks about. A principle so fundamental that nearly every force in nature depends on it, yet most people have never heard of it. It's called gauge theory, and it's probably the most important idea in 20th century physics that isn't relativity or quantum mechanics. But here's what they don't tell you. Gauge theory says that most of what we think is real isn't actually real at all. I'm going to explain something that took me years to fully appreciate. The electromagnetic field, the thing that carries light and radio waves and holds atoms together, doesn't exist in the way you think it does. Neither do the forces that hold atomic nuclei together or the mechanism behind radioactive decay. All of these arise from something stranger and more abstract. They arise from redundancy in our description of nature. That probably sounds insane. How can forces come from redundancy? How can something as tangible as electricity emerge from an abstract principle about mathematical descriptions? But that's exactly what gauge theory tells us. And once you understand it, you realize that the universe operates on completely different principles than common sense suggests. Let me start with what gauge theory actually is. At its core, it's about symmetry, not the kind of symmetry you see in a snowflake or a mirror, mathematical symmetry. Specifically, it's about transformations you can make to your equations that don't change any physical predictions. And here's the key insight. Nature seems to be built in such a way that these symmetries aren't just mathematical conveniences. They're fundamental. They determine what forces exist. The first gauge theory was electromagnetism. Maxwell figured out the equations in the 1860s, but he didn't realize what he had. It took another 50 years before people understood that electromagnetism has a gauge symmetry. You can change the electromagnetic potential in certain ways without changing the electric or magnetic fields. Different potentials can describe the exact same physical situation. Now, you might think that means the potential is just a mathematical artifact, something we invented to make the calculations easier. And for a long time, that's what people thought. But then quantum mechanics came along and everything changed. In quantum mechanics, the potential is real. Electrons respond to it directly. There's an experiment called the Aharonov-Bohm effect that proves this. You can shield an electron from all electric and magnetic fields, but if there's a potential present, the electron's wave function still changes. The potential affects reality even when the fields don't. So which is it? Is the potential real or is it arbitrary? The answer is both, and that's what makes gauge theory so strange. The potential is real in the sense that it affects physical outcomes, but it's also arbitrary in the sense that you can change it without changing those outcomes. How can something be both real and arbitrary? This is where the concept of gauge invariance comes in. Physical laws have to be written in a way that doesn't depend on your choice of potential. Any observable quantity has to be the same no matter which potential you use. That constraint, that requirement of gauge invariance, is incredibly restrictive. It basically determines the entire structure of electromagnetism. Think about that for a moment. We're saying that the requirement that unobservable things remain unobservable is so powerful that it forces the theory to have a specific form. The symmetry doesn't just describe the physics, it generates it. And here's what nobody tells you. The photon exists because of gauge symmetry, not the other way around. We usually think the photon is fundamental and gauge symmetry is just a property it happens to have. But it's deeper than that. Gauge symmetry requires that there be a massless spin-one particle. That particle is what we call the photon. The force of electromagnetism exists because nature has this particular symmetry. Let me say that again differently. Light exists because the universe has a certain kind of redundancy in how it can be described. The electromagnetic force, everything from radio waves to X-rays to the bonds between atoms, all of it emerges from a mathematical symmetry, not from particles pushing and pulling, from symmetry. Does that sound backwards? It should. We're used to thinking that particles and forces are fundamental, and mathematics is just how we describe them. But gauge theory suggests it's the other way around. The mathematics, the symmetry, is fundamental. The particles and forces are consequences. Now, electromagnetism is just the beginning. Once physicists realized that gauge symmetry underlies electromagnetism, they started looking for other gauge theories, and they found them. The strong nuclear force, the one that holds protons and neutrons together, is a gauge theory. The weak nuclear force, the one responsible for radioactive decay, is a gauge theory. Even gravity might be a gauge theory of a certain kind. We call the modern framework the Standard Model. It describes all known particles and forces except gravity, and it's built entirely on gauge symmetry. There are three gauge symmetries corresponding to the three fundamental forces. The electromagnetic force comes from what we call U1 symmetry. The weak force comes from SU2 symmetry. The strong force comes from SU3 symmetry. Those labels might not mean anything to you, but here's what matters. Each symmetry requires the existence of certain particles. U1 requires one massless particle, the photon. SU2 requires three particles, the W and Z bosons. SU3 requires 8 particles, the gluons. The entire structure of the Standard Model, every particle and interaction follows from these symmetries. And here's the thing, we didn't choose these symmetries because they matched observations. We found them by following the mathematical logic of gauge theory. The symmetries predicted the particles before we discovered them. The W and Z bosons were predicted in the 1960s and found in the 1980s. The gluons were predicted in the 1970s and confirmed shortly after. Gauge theory told us what to look for. But let's get back to what you're never told. The most important fact about gauge theory is this. The gauge field, the thing that carries the force, is not uniquely defined. There are infinitely many different gauge fields that describe the same physical situation, and nature doesn't choose between them. All of those descriptions are equally valid simultaneously. This is completely unlike anything in everyday experience. Imagine if I told you that your position isn't uniquely defined, that there are infinitely many different coordinates that all describe where you are and nature doesn't pick one. You'd say that's nonsense. Coordinates are arbitrary, but position is real. But in gauge theory, it's the opposite. The gauge field is like the coordinates. It's the thing we use to describe reality, but it's not reality itself. So what is reality? What's the thing that's actually real if the gauge field isn't? The answer is what we call gauge invariant quantities, things like the electric and magnetic fields in electromagnetism, or the field strength tensor if you want to be more general. These are combinations of the gauge field that don't change when you change your gauge choice, and only these gauge invariant quantities correspond to observable physics. Everything else, all the other components of the gauge field, are redundant. They're degrees of freedom in our description that don't correspond to degrees of freedom in nature. And here's the remarkable thing, that redundancy isn't a flaw in our description. It's essential. Without it, the theory wouldn't work. The mathematical consistency of gauge theory requires that redundancy. Why? Because of quantum mechanics. When you quantize a gauge theory, you run into problems. The math becomes inconsistent. You get infinities and contradictions. But if you maintain gauge symmetry, if you keep all that redundancy, the inconsistencies cancel out. The redundant degrees of freedom are precisely what you need to make the quantum theory consistent. This was discovered in the 1950s and 1960s, and it was shocking. It meant that the unphysical parts of the theory, the parts that don't correspond to reality, are necessary for the physical parts to work correctly. You can't get rid of the redundancy without destroying the theory. Let me give you a concrete example. In quantum electrodynamics, the quantum version of electromagnetism, photons can be polarized in different ways. If a photon is moving in the z direction, it can be polarized in the x direction or the y direction. Those are the two physical polarization states, but mathematically there are four polarization states. Two of them are unphysical. They don't correspond to real photons you can detect. So why do they exist in the math? Because the gauge symmetry requires them. The theory needs those extra states to be consistent. When you calculate scattering amplitudes, the probabilities for particles to interact, the unphysical states contribute. Their contributions cancel out in the final answer, but you need them during the calculation. Without them, the theory gives nonsense. This is what I mean when I say most of what we think is real isn't real. The gauge field has components that exist mathematically, but not physically, and those components are essential for making predictions about the components that do exist physically. Reality and description are tangled together in a way that's impossible to separate cleanly. Now here's where it gets even stranger. The redundancy in gauge theory isn't just mathematical bookkeeping. It has physical consequences. One of them is charge conservation. The fact that electric charge can't be created or destroyed, that the total charge in a closed system never changes, is a direct consequence of gauge symmetry. This connection was discovered by Emmy Noether in 1918. She proved a theorem that says every continuous symmetry corresponds to a conservation law. If your theory has a symmetry under time translation, then energy is conserved. If it has a symmetry under space translation, then momentum is conserved. And if it has gauge symmetry, then charge is conserved. So charge conservation isn't a separate law of nature that we discovered empirically. It's built into the structure of gauge theory. It has to be true if gauge symmetry is true, and gauge symmetry has to be true if we want a consistent quantum theory of electromagnetism. The whole thing is locked together. But wait, it gets better. Gauge symmetry doesn't just give you conservation laws, it gives you interactions. In fact, it forces interactions to exist. Let me explain what I mean. Suppose you have a theory of electrons without any forces, just free electrons moving through space. That theory has a global symmetry. You can change the phase of all electron wave functions by the same amount everywhere, and the physics doesn't change. That's a symmetry, but it's not a gauge symmetry because you're doing the same thing everywhere. Now, suppose you want to make that symmetry local. You want to be able to change the phase by different amounts at different points in space and time. That sounds like a small change, but it has enormous consequences. Because when you do that, the theory is no longer consistent. The equations break. How do you fix them? You have to add a new field, a gauge field, and that field has to interact with the electrons in a very specific way. The interaction is completely determined by the requirement of gauge invariance. You don't get to choose it. The symmetry dictates the form of the interaction. And what does that interaction look like? It's exactly the electromagnetic interaction. The gauge field you had to add is the electromagnetic field. The photon emerges as the carrier of the force that's required to maintain local gauge symmetry. This is the sense in which gauge symmetry generates forces. You start with matter, electrons in this case. You demand local gauge symmetry, and you're forced to introduce a force field. The properties of that field, its interactions, its dynamics, all follow from the symmetry. This is called the gauge principle, and it's how we construct all the fundamental forces. The strong nuclear force works the same way. You start with quarks. You demand a different kind of gauge symmetry, SU3, instead of U1. And you're forced to introduce gluons, 8 of them, because that's what SU3 symmetry requires. The interactions between quarks and gluons are completely determined. You don't have freedom to adjust them. And here's what's remarkable. Those interactions have properties that no one expected. Gluons interact with each other. Photons don't. In electromagnetism, only charged particles interact with photons. But in the strong force, the gluons themselves carry the charge. They interact with each other directly. and that leads to bizarre phenomena. One is called confinement. Quarks can never be isolated. You can't pull a single quark out of a proton no matter how hard you try. The more you pull, the stronger the force gets. It's like stretching a rubber band, except the band never breaks. Eventually, you put in enough energy that new quarks pop into existence, and you end up with multiple bound states instead of free quarks. Nobody predicted this. It emerged from the mathematics of SU3 gauge theory. People calculated what the theory predicted and found confinement staring back at them. And then experiments confirmed it. We've never seen a free quark. They always come in bound states. Gauge theory explained why. Another strange property is asymptotic freedom. At very short distances or very high energies, the strong force gets weaker. Quarks that are close together barely interact. This is the opposite of what happens with electromagnetism, where charges that are close together interact more strongly. But it's what SU3 gauge theory predicts, and it's what we observe. These discoveries earned the Nobel Prize in 2004. Asymptotic freedom was completely unexpected, but it fell right out of the equations once people worked them out carefully. The gauge principle doesn't just describe nature. It predicts aspects of nature that seem to contradict intuition. Now let me tell you the thing about gauge theory that bothers me the most. We don't know why it works. We know that it does. We've tested it to incredible precision. The predictions of quantum electrodynamics have been confirmed to 1 part in a billion. The Standard Model has passed every experimental test we've thrown at it. But we don't know why nature chose gauge symmetry as its organizing principle. Is it fundamental or is it emergent from something deeper? Some physicists think gauge symmetry is the deepest level. Others think there's a more fundamental description, and gauge theory is an approximation that works at low energies. We don't know. And that uncertainty makes gauge theory both powerful and mysterious. What we do know is that gauge theory changed how we think about forces. Before gauge theory, forces were things that particles exerted on each other. Electromagnetic repulsion, gravitational attraction. You had particles, and separately you had forces acting between them. After gauge theory, we understand that forces aren't separate from matter. They're required by the symmetries that matter obeys. You can't have electrons without photons. You can't have quarks without gluons. The matter and the forces are two aspects of the same underlying structure. And that structure is deeply quantum mechanical. Classical gauge theories exist, but they're missing the most important features. It's only when you quantize them that you see things like charge conservation from symmetry, or asymptotic freedom, or the requirement that gauge bosons be massless. Actually, that last one deserves more attention. Gauge symmetry requires that the force carriers be massless. Photons are massless, gluons are massless, but the W and Z bosons have mass. How does that work? The answer is one of the great triumphs of 20th century physics. The weak force does have gauge symmetry, but that symmetry is hidden. It's spontaneously broken by the Higgs field. The Higgs field has a non-zero value everywhere in space, and when gauge bosons interact with that field, they acquire mass. But the gauge symmetry is still there. It's just not manifest. The equations still have the symmetry, even though the solutions don't. This is called spontaneous symmetry breaking, and it's how we explain why the weak force is weak. The W and Z bosons are heavy, so the force they carry only acts over short distances. The Higgs mechanism was proposed in the 1960s. The Higgs boson was finally discovered in 2012. 50 years of searching to confirm a prediction that came from gauge theory. And it worked. The Higgs exists. It has the properties we predicted. Gauge symmetry, even when it's hidden, determines the structure of reality. So here's what you're never told about gauge theory. It's not just a mathematical trick. It's not just a convenient way to organize the equations. It's the deepest principle we know. It tells us that the universe has redundancy built into its fabric, that multiple descriptions can correspond to the same reality, and that the requirement for consistency between those descriptions is what generates forces. Every force in the Standard Model comes from gauge symmetry, electromagnetism from U1, the weak force from SU2, the strong force from SU3. And those aren't arbitrary choices. They're the simplest non-trivial symmetries you can have. Nature picked the most economical structure consistent with the particles we observe. Could there be other gauge symmetries we haven't discovered? Maybe. People have looked. We've searched for additional forces, additional gauge bosons. So far, we haven't found any. The Standard Model seems to be complete at the energy scales we can access, but there could be more symmetries at higher energies. Grand unified theories propose that all three gauge symmetries merge into one at extremely high energies. We don't know if that's true, but it's possible. And what about gravity? Einstein's general relativity is a gauge theory of a different kind. Instead of internal symmetries like U1 or SU3, it has symmetry under coordinate transformations. You can change how you label points in spacetime, and the physics doesn't change. That's a gauge symmetry, and it requires the existence of a massless spin-2 particle, the graviton. So all four fundamental forces might be gauge theories. If that's true, then the entire structure of physics, everything from photons to black holes, comes from redundancy and symmetry, from the principle that unphysical degrees of freedom must remain unphysical. I find that astonishing. The universe could have been built in many ways. It could have had forces that don't come from symmetry. It could have had matter without